In this lesson, we're going to be talking about how to evaluate and graph polynomial functions. But before we do that, we need to know exactly what is a polynomial function. And a polynomial function is in the form of f of x equals a sub n, x to the n, plus a sub n minus 1 to x to the n minus 1 plus dot 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 a sub 1 x plus a sub 0, where the a's represent coefficients, the a sub n and n minus 1, and the x are your variables, and then the n's represent your exponents. So, and then the dot 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 means there can be a whole bunch of other terms in between there. It can be any number of terms. And the final a sub 0 here simply means that it is a constant. So, for instance, the way you could read this is if I had a sub n here, this is known as my leading coefficient. Okay, so the very first coefficient, and then n here is the exponent on the first term, and that's known as the degree of the polynomial. And then we talked about a sub 0 being the constant. And this is known as the standard form of a polynomial. It's also important to point out that the exponents are in descending order. Hence, if n is 5, then this would be 5 minus 1, which would be 4. So it would look something like this. F of x equals, so let's say a sub n is 2, then x to the n power, let's call it 4, plus, and then our next term, a sub n minus 1, let's say that's just going to be simply a different coefficient there, and then x to the, and then this tells us n minus 1, where n is 4, so n minus 1 is going to be 3. That's all it's saying. You're just subtracting 1 from it. And then the next one is going to be, let's say just another number like negative 5, and then it's going to be n minus 2, so this would be 2, and then let's say 6, and then this is going to be n minus 3, so that's just going to be x, and then we'd have some sort of constant, like plus 1. So the leading, this would be the leading coefficient, which I'll abbreviate as LC, and this represents the degree. And the 1 is my constant. Now, there are different types of polynomial functions. You are going to want to write this down because you're going to be responsible, well, you're going to be held accountable for knowing the degrees from 0 to 4, as well as knowing the types. So you'll need to know the names, as well as how to spell them correctly, what the standard form looks like, and here are some examples so you can see what that looks like. So if something has a degree of 0, that means you have x to the 0th power, which is just 1, and so that's just going to be a constant. So f of x is equal to a sub 0. So for instance, if I had f of x is equal to, let's say, negative 14, and then since the degree is 0, I could say x to the 0th power, which is just 1, so then f of x would equal just negative 14. So that's just a constant. That's going to be a horizontal line if we were to graph that. Linear, this is your, this is just like y equals ax plus b, except we're in standard form as a polynomial. It's f of x equals a sub 1x plus a sub 0. So, this is just like ax plus b, but we're replacing a with a sub 0, and we're replacing b I'm sorry, we're replacing a with a sub 1, and then we're replacing b with a sub 0. So, and we know what a line looks like, f of x equals 5x minus 7. And then we've talked about quadratics, and quadratics would be, in standard form. We recognize standard form previously as y equals ax squared plus bx plus c, but we're going to replace the a, b, and c with a sub 2, a sub 1, and a sub 0 respectively. But so that's what the quadratic looks like. So we're going to bring in two new ones, known as a cubic, where it has a degree of 3, as we can see here. And in the example, we can see there's the degree of 3, and the leading coefficient on this one is going to be 1, even though we don't see it. It's 1, and the constant here is going to be 0. So because we don't see any constant there, it must be plus 0. And then finally we have a quartic, and a quartic function has a degree of 4. So an example of a quartic function would be f of x equals x to the 4th plus 2x minus 1. Notice that we don't have an x cubed or an x squared term on this example, but it's still quartic because the largest degree or the largest exponent is 4, so it will still look like a quartic function. Example 1 says decide whether a function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. Well, in order for something to be a polynomial function, we have to have integers, or I should say positive integers, as exponents. So in other words, we're looking at natural numbers. We're not including 0. So if I look at a here, this has a exponent of 1/2, and this has an exponent of 1. Well, because we have an exponent of 1/2 here, this is not going to be a polynomial function. So no, not a polynomial function. This next one, b, I'm looking at all the exponents. I have a 5 and a 2 and a 4, and notice it's not in descending order, so it's all mixed up. It's not in proper form. And then we have the square root of 10, but that's just a constant, and that's okay. It's just going to be some number. So this is a polynomial function, so yes, it is one. And in standard form, we need to write it in descending order. So I'd say g of x is equal to negative 8x to the 5th plus x to the 4th minus 4x squared, and then our constant square root of 10. So the degree on this is 5, and so we just say this is a 5th. So anything beyond quartic, I'm not going to make you know the name. We'll just call this the name is going to be a 5th degree polynomial. FY, poly meaning many, nomial meaning nomial, I guess, many nomials, whatever a nomial is. This particular polynomial has 1, 2, 3, 4 terms, or 4 monomials, so a single, mono meaning single nomial. So this would be 5th degree. Like I said, anything beyond 4, I'm not going to make you, come up with a name for that. So if it's 6, as a degree of 6, 6th degree, 7th degree, so forth. And the the leading coefficient, I'll just abbreviate that, so the leading coefficient in this case is going to be a negative 8. In C, this, if I look at this, it does look like a polynomial because all the exponents are natural numbers. So I would say yes. I'd also note that it's already in standard form. So I would say f of x is equal to x cubed minus 4/5 x squared minus 1. The degree is 3. This is a cubic. That's the name of it. And our leading coefficient is going to be a positive 1. Now, the last one, I look at it and I'd say, oh, well, I notice here that we have a 4, a negative 2, there is no exponent, and a 4. But remember that the exponents, and we want to let's make note of this, exponents must be natural numbers in order to be a polynomial. Well, the negative 2 here is not a natural number, so this one would not be a polynomial. One of the other things we're going to do is use direct substitution to evaluate a polynomial. So this is just simple, using a function. So we want to substitute in 2 for x, or evaluate what this polynomial function is going to be when our input is 2. So we would say f of 2 is equal to negative 3 times 2 cubed plus 2 squared minus 12 times 2 minus 5. And then we're just going to solve it, or simplify it rather. And that's going to be negative 3 times 8 plus 4 minus 24 minus 5. And then we multiply negative 3 and 8. That's going to give us negative 24. We're going to add 4, gives us negative 24. And we work this whole thing out. It should come out to be negative 49. So f of 2 equals negative 49. Okay, now polynomials have end behavior. Actually, all functions have end behavior. These polynomial functions, we can determine the end behavior based off the equation. What end behavior is we're looking at and exploring, what happens as the polynomial, we have the curvy stuff in the middle, and then what happens as it, approaches infinity, how does it finish off? What does it keep doing? So at the right end as well as the left end. So this is known as left end behavior, and on the right side is known as, right end behavior. And it's just going to keep, heading in that direction, for infinity after all the curvy stuff in the middle is taken care of. So if the degree of our polynomial is odd, and the leading coefficient is positive, then what we say here on the right side is that f of x, which corresponds with the y, f of x is approaching positive infinity. So we write it just like this. F of x is approaching positive infinity as our independent variable x approaches positive infinity. So as we're going to positive infinity in this direction, it's going to positive infinity in this direction. And that's when it's odd and positive. And then in the other direction, as f of x, or f of x is approaching negative infinity, so it's going down to negative infinity as x approaches negative infinity. So it's going down and to the left. And we would express it this way. If the degree is odd, but the leading coefficient's negative, it simply reflects. So this way, on the right side, f of x is approaching negative infinity as x approaches positive infinity. And the left end behavior, f of x is approaching positive infinity as x approaches negative infinity. So it's going up as it heads further to the left. And anything that's odd degree, it's going to end that way. As one arrow's going up, the other arrow's going down, or as one end, end's going positive, the other one's going towards negative on the y. Whereas if it's even degree, it's going to both sides are going to both end up going up, or they're both going to go down. So if it's an even degree and it's positive, they're both going to go up. So we would express that as f of x so the right end behavior as f of x approaches positive infinity as x approaches positive infinity. And then on the left end behavior, f of x approaches positive infinity as x approaches negative infinity. So as it's going to the left, it's going up, and as it's going to the right, it's also going up. And then if the degree is even but it's negative, it's going to open down. A good way to kind of think about how end behavior is think about what happens in the simplest case, like the simplest polynomial. For instance, an odd degree polynomial a simple odd degree polynomial is going to be something that's linear. Okay, a line has a degree of 1, and 1 is odd. So if you have a positive slope, let's say I have something like y equals 2x, okay, well, and I'll just add like a plus 1. So if this is my my axes, then if it's positive, we know it goes up. And look, as on the right side, as f of x approaches positive infinity, so it's going up in the y, x is approaching positive infinity. And see, it's going down. As it goes further to the left, f of x approaches negative infinity, it's going down, x is approaching negative infinity. So think of it as a line. And then if the slope is reversed, so let's say the equation is y equals negative 2x plus 1, then if I were to graph that, the line would just, head in a negative direction. So it's going to do something like this. And see, it matches up. As f of x approaches negative infinity, x approaches positive infinity. And as f of x approaches positive infinity, so it's heading up on the y as it goes further to the left. So think of it that way. And in this one, the simplest even degree polynomial is going to be a quadratic. A parabola that has a positive leading coefficient, or a value, is going to open up. And notice that it's going to have the same general look, other than the little curvy stuff in the middle. It's going to be, it goes up as x goes to infinity, and then it goes up as x goes to negative infinity. And then with a parabola, if the leading coefficient is negative, it reflects and it opens down. So then we can see as x approaches positive infinity, f of x approaches negative infinity. So as we go further to the right, so if this is my axis, as it goes further to the right, it's going to go down, and as it goes further to the left, it's also going to go down. So again, think of, if you get confused, if you look at the equation, think of the simplest case. The simplest odd degree is a line, so it's going to have the same n behavior as a line, and your polynomial is going to have the same n behavior as a parabola if its degree is even. So let's take a look at an example here. So it says, what is true about the degree and leading coefficient of a polynomial function whose graph is shown? Okay, so this one, they just give us the graph, and I can see that this is going to be, well, it's similar to a line. So as far as, it's going in one direction, it's going up, and then it's going down. And so a line would be something like this. And this tells me that is a positive slope line, so that tells me that this polynomial is going to have a positive leading coefficient. So the leading coefficient is positive, so we'll say positive leading coefficient, and we know that it's odd. So, and we'll say, and has an odd degree. Our final example is going to be graphing a polynomial function. So we've done lines, we've done quadratics, now let's do everything else. And the process is going to be largely the same. So I have a quartic function here, and we're going to use a calculator to assist us with this, as opposed to just building a table by hand. We can do that. We can plug in a whole bunch of numbers, negative, positive, 0, and plot out the points and connect them. But we'll go ahead and use a calculator to assist us with that. So I went ahead and I put it in my y equals x to the negative fourth minus x cubed minus 4x squared plus 4. And if I graph it using my default window, it looks like this. Now, I'm not going to do a sketch. I want a fairly accurate graph, okay? I'm not just going to say freehand and say, oh, it does this, it's about like this. I need some solid points to use. And I'm going to go through the things that I'll be looking for when you're graphing a polynomial function. I have a pretty good window as far as seeing the graph, but I do have a lot of extra space on the left and right, so I'm going to change my window a bit so I can get a better view for this. I don't need so much on the x minimum, so instead of negative 10, I'll go ahead and make that negative 6, and on my x max, instead of being 10, I'll make that positive 6, and we'll graph it that way. Okay, so I got a much better view of this graph, and I want to have a good look so I can see the maximums, the local maximums and the local minimums. And what a local maximum and a local minimum is, if I were to look at this graph here, I see that I have a local minimum right about here and here, but I would have another local minimum right here. So these two dips are known as local minimums, and this is known as a local maximum. So we want to find all these various points. So to do that, I'm going to go ahead and use the calc feature on my graph. So I'm going to use option 3, and we'll start with the first local minimum where it curves down here. So I'll set my left bound and then I'm going to do my right bound, and then guess. I'll just press enter, and that looks to be, well, that's at -1 and +2. So I'll plot a point at -1, +2. Okay, so I know that that's going to be a local minimum. Then I'm going to label that point so that I know it is a local minimum. So -1, +2. So be sure you do that. Then I'm going to find my next local, and now I'll do a local maximum. So here's a local maximum, this little hump here, so I'll press enter, and here, so it's like the top of the hill. We just want just on either side, just to the left of it and just to the right of it, and that's at 0, 4. So I'll go to 0, 4 and plot a point, and I'll label that 0, 4. And then we'll hit the next local minimum. So second calc, that's going to be minimum. And then I'm going to go to the left, that point, press enter, and go to the right, press enter, and there it is at 2, 4. So 2, 4 to -4. So right here, and I'll label that to -4. So be sure you label all your local minimums and local maximums. I will be looking for that. Now we need to get some points in between, and we can just use our table for that. So I'm going to go second table, and we want to get any point that's reasonable on our graph. So like -3 and 76, that's going to be way off our graph. But we could do like -2 and 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it's going to be off my graph, so I'm just going to estimate a little bit. So I would extend my graph if I could, but that's going to be up here. And I already have -1 and 2 when we found the local minimum. When we found that local minimum. And that's not always going to be the case, that it's going to be 2 integers for the x and the y. More likely you're going to get some weird decimal. We have 0, 4. Let's plot 1, 0. So 1, 0. Right here, that's going to be an x-intercept. And then we can hit, we already have 2, -4, and then 3 and 22. That's not going to fit into our graph. We know that's just it's going to go like straight up. So we're going to go ahead and connect those points, and it's going to look roughly like what we have on the calculator. Not exactly, because the window is going to be different than what we have here. So I'll start up at this point here, come down to this local minimum, make our first turn. Then we go to the local maximum, make our next turn, go through this point, straight down best we can, get to this local minimum, and then we're going to go up really fast because the 3 it's just going to be practically vertical. Really hard to write in this thing, and it's going to go end up here. Then we'll put an arrow here and here, and do not forget that, or let me tell you, you will also write down the end behavior on your graphs. So we'll say x on this side approaches negative infinity, or f of x, let me write this properly, f of x approaches positive infinity as x approaches negative infinity. And on this side, we'll write f of x approaches positive infinity. I'll just write the infinity sign. But make sure that you write negative infinity to differentiate that it is negative. I'll go ahead and put the plus. As x approaches positive infinity. Okay, so make sure that you have all local minimums and maximums, any other points that are reasonable on your graph, as well as listing out the end behavior, and don't forget those arrows. All right, so that's evaluating and graphing polynomials, and I'll see you on the flip side.